Alrighty, so in this video we're going to take a look at the June 2003 Unified paper, starting off with some common misuses of physics in the media. This isn't a thing just in 2003, it pretty much happens all the time, so let's take a look. So first statement, the heat of the oven should be 180 degrees. A lot of cookbooks say that. Obviously what it means to say is that the temperature of the oven should be 180 degrees. We use the word heat to describe the transfer of energy from one place to another, but we talk about the temperature of an oven. Global warming could cause a rise in sea temperature of 5 degrees Celsius or 278 Kelvin in the next 100 years. The 5-degree temperature change is incredibly reasonable. That is what some of the models say, but that would also be a 5 Kelvin temperature rise. The degrees are the same size in both scales. Okay, so items of weight greater than 0.75 kilograms cannot be posted second class. Not too many people these days, I guess, are posting. Most people are emailing, but you should still say that the mass would be in 0.75 kilograms, not the weight. That would be in newtons. The power output of a power station is 500 milliwatts. That would be an absurdly useless power station producing less than 1 watt. It's presumably meant to have been 500 megawatts, which is a very typical power station power output there. The pressure on the floor is 5 tons. Tons is a unit of mass, not pressure. We either want the mass was 5 tons or the pressure was in pascals, but not that combination. Once out of the Earth's atmosphere, the astronaut was weightless. Complete nonsense. Gravity is an infinite range force, so you cannot possibly be weightless. But what could be happening is the astronaut is in a state of free fall, so it appears to them that they are weightless because they are accelerating at the same rate their spaceship is. The cricketer transferred his weight from his right foot to his left foot. No, again, nonsense. Your weight force acts from your center of gravity, which is in a fixed location. What you're actually doing is transferring the normal contact force from the ground between your feet when you step from one foot to the other. All right, so let's get on to question 2. Explain what's meant by a vector, a property of magnitude and direction. Underline the following quantities, which are vectors. So mass is a scalar, has magnitude. Displacement would be a vector. I appreciate that it says underline, but I want to be clear for this video. Magnetic flux density is another way of saying magnetic field strength, which is also a vector quantity. Density is a scalar. Weight is a force, so it's a vector. Time is a scalar. Distance is a scalar. All kinds of energy are scalars, so those are the only 3. Okay, so we've got a car of mass 600 kilograms, changes velocity in 3 different ways, as we can see here. Calculate the magnitude and direction of the momentum change in each case. So let's do that. So the mass is going to be the same before and after, so we can factorize it out, which I did straight away. So 600 in every case. And change is always final minus initial. So that's why it's 40 minus 10. That's why it's, or minus 40 minus 10, or 10 minus 40, because it's final minus initial. So we can see that the first one is going to be to the right, like all the initial velocities, but the second 2 are negative, so they're going to be to the left. Okay, so give an example of a situation where 2 vectors other than velocity or momentum are added. So a very simple one would be when we calculate a resultant force, but maybe also to calculate a resultant displacement as well. We could do that too. Give an equation expressed in words in which a scalar quantity is obtained by multiplying 2 vectors. So there are 2 that I can think of. Power equals force times velocity, and work done is force times displacement. Power and work done are both scalar quantities because they're associated with energy, but force, velocity, and displacement are all vector quantities. Okay, so moving on to a scenario-based question. We're looking at an electric motor, and it's a specific type called a shunt wound motor. That's all information which is utterly meaningless in terms of the question. They're just dumping information at you to try and confuse you. So the key information is connected to a 12-volt supply, and we've got a circuit diagram coming on the next page to show us what this looks like as an electric circuit. So the first question asks us to label on the diagram the direction of the forces acting here. So I'm going to show you before we move any further. So the two forces would be in these directions. So I'm using Fleming's left-hand dynamo rule. The field is going from left to right. At the top of the armature, the current is coming out of the page or towards you, so you can see that the force would be upwards, whereas at the bottom, the current's going into the page, which is why the force is downwards. Okay, so like I said, we've got a diagram of the setup here. So first, I'm just going to explain the answer to part A. We used Fleming's left-hand dynamo rule to get the direction of the forces there. Okay, so let's do some work. So we're going to be using the information from the diagram, so flip back to it if you need it. So when offload, it's found the current from the supply is 3 amps. So offload meaning we're not doing anything with it. So show that the current in the electromagnet is 0.5 amps. That's fairly straightforward using Ohm's law. We know the potential difference is 12. We can see from the diagram the resistance is 24, giving us a current of 0.5. So if the current coming out the power supply is 3, that would mean the current going through the armature is 2.5 amps, because we're just using Kirchhoff's first law. Then we want to calculate the power supplied by the power supply. So we know the current coming out of it, we know the potential difference, so that's fairly straightforward, 36 watts. Okay. So calculate the power wasted as heat in the electromagnet. Again, we know the current, we know the potential difference, it's 6 watts. And then in the armature resistance, I'm going to use a different equation here, because at the moment we don't know what the potential difference is across the armature resistance, because we don't know what the potential difference is across the armature as well. So this is why I'm going to use I squared R, because we already know the current going through it, we know its resistance, so we can get its power. And using all of these powers, we can figure out what the power used by the armature is, using essentially conservation of energy. Okay, so now we're going to use conservation of energy to explain why in the first few seconds of operation, or after, so the first few seconds of operation, the electromagnet is not using power to produce a magnetic field. So once you've produced the magnetic field, it's now a stable magnetic field, and that means we're not storing any more energy in the magnetic field once we've got a stable one. And that means we're not going to be using any power in the electromagnet anymore. So explain in terms of conservation of energy why the armature current is not 6 amps. So people get 6 amps because they go, well, the potential difference is 12, the armature resistance is 2, so we should get a current of 6. Firstly, that violates Kirchhoff's current rule because it started as 3, but it asks us to do conservation of energy. So the reason it's not 6 amps is because not all of the 12 volts is dissipated by the armature resistance. Some of it is dissipated by the armature in terms of mechanical power as well. So because it's rotating, the armature is producing mechanical power as well. But if it was 6 amps, what would that would mean that all of the energy is being transferred by the resistor into thermal energy. And then finally, explain using conservation energy why power is required by the armature to drive it. So even when you're at constant speed and it's not accelerating, we're still doing work against air resistance and friction, so we're gonna need power for that purpose. Okay, so if too much load is put on the armature, it may stop rotating and the current starts to increase. That's because we're no longer using any power in the armature, so more of it is transferred to thermal energy in the armature resistance. Calculate the total current supplied by the motor. So now all of the 12 volts is across the armature resistance. So there's a current of 6 amps going through the armature, but there's still 0.5 going through the electromagnet, giving us a total current supplied of 6.5 amps. So explain why the motor can burn out when the armature is stationary. So we can look at the amount of thermal energy that is being dissipated by the armature resistance. 72 watts, which is quite a chunk of energy that's being dissipated as heat. Wire is typically wrapped in an insulator. So if the wire starts getting very hot, what's going to happen is you melt the insulator, which is going to be a problem in terms of your setup there. Okay, so final question. Equilibrium is frequently used in mechanics and structural engineering. Which two conditions are necessary for a body to be in mechanical equilibrium? So this is from mechanics topics. Resultant force must be zero, and the clockwise moment must be equal to the anti-clockwise moment. Those were our two conditions. Why is it important the bridge designer considers the mechanical equilibrium of a bridge during and after construction? So when you're building a bridge, the load on it is going to be much smaller because you don't have cars and that kind of thing on it. Whereas once the bridge opens, you're going to have trucks, cars, buses, and a massive load on it. And what that's going to do is it's going to change the way the forces are distributed on the bridge and the size of the forces. And you need to make sure it's safe when people are building the bridge, because otherwise you'll kill people, but you need to make sure it's safe when it's being used as well. So we have to consider both parts. And actually these days, designers also have to consider the safety during the demolition of the bridge as well. Okay, so the term dynamic equilibrium does not appear in your physics specification, but it can be applied to a moving object such as an aircraft. Consider a condition which applies if an aircraft is in dynamic equilibrium. So I think there are two that you could use. The thrust force forward is equal to the air resistance and lift force equal to the weight force. So it's traveling at quite high speed, but all the forces are in equilibrium. Thermal equilibrium is used as another idea. Give examples in everyday life of an object in thermal equilibrium with the surroundings. So if you head to your kitchen, you'll find a couple. So if you put stuff in an oven, it will become the same temperature as the oven. Or if you put stuff in a fridge, again, your stuff will become the same temperature as the fridge. Those would be some fairly straightforward examples. Things that are not, if you put a hot object out, so if you leave your coffee sitting on a table, that's not going to be, and it's going to be radiating energy to the surroundings. And we ourselves are not in thermal equilibrium either. We are generating heat. We are hotter than our surroundings, so we are not in thermal equilibrium. Finally, a longer answer question looking at global warming. So use your knowledge of the electromagnetic spectrum in relation to the transfer of energy to outline how the mean temperature of the Earth's surface is related to energy gains and losses. Okay, so let's first talk about where the Earth is gaining energy from. So we're receiving thermal energy in two forms, in infrared radiation from the sun, because most other wavelengths, apart from visible, are filtered out by the ozone layers and stuff. And that is focused on different parts of the Earth. So depending on which part of the Earth is facing the sun, that energy gets focused on different parts. But we are also getting thermal energy transferred from the center of the Earth as well. It's much hotter there. So we've got two sources of thermal energy arriving on the surface of the Earth. But the Earth is also emitting thermal energy through infraradiation to outer space. So the Earth is hotter than the space around it, so it's emitting radiation. But it's going to be a longer wavelength of radiation because the Earth is not as hot. Essentially what I'm using there is Wien's displacement law there. Because the Earth is cooler, the wavelength is going to be longer that it emits. So in terms of global warming, there's a third process that matters, is that the Earth's infrared radiation is being reflected back to the surface by greenhouse gases, methane, water vapor, carbon dioxide. And what that's doing is that's essentially trapping the more thermal energy on Earth. And if the total amount absorbed by the surface of the Earth from all of these sources is greater than the amount emitted into outer space, the internal energy of the Earth will increase and therefore the temperature will rise. So if you want to have a stable temperature, you need all of these processes to be in balance, which they have been for a long period of our history, But now the CO2 concentrations increased, they are not, and we're starting to get to the point where the internal energy and the temperature is rising. Okay, so that concludes this unified physics paper. I hope you found it useful to go through the answers to each of these questions. If you have any questions having seen the answers, please do comment and let me know. But thanks for taking the time to watch.